One is relations and functions. First off, definition of a relation. A relation is any set of ordered pairs or points. The phrase ordered pairs and points can be interchanged. They mean the same thing. I've given you an example of a relation. It happens to be a set of ordered points, ordered pairs, points. We're going to use this example now, and we're going to use it again here in a little bit, so you'll be able to copy and paste it and save you a little bit of time here in a minute. This first slide is all about getting us on the same page regarding some terminology. I believe much of what you're going to see in this first slide is not new. For example, every relation has a domain and range. I believe you have experience with domain and range. Some of your experiences may be smaller than others. But this gets used. Domain and range gets used the rest of this year. In most of your high-level math classes, you need to know about domain and range and what it is. Okay, so today I'm going to help define that for you in case you're unsure. Okay, the domain is the set of all x coordinates. What's the next sentence going to be? Just say it. Very good. Copy paste, change the word from domain to range and x to y. Same thing. Same basic structure anyway, right? Domain are the x's, range are the y's. However you need to keep that straight, D comes before R in the alphabet, X comes before Y, if that's how you want to think about it. Now, as some of you have begun to learn, I'm a little nitpicky about things. And one of the things I'm going to be nitpicky about is how you write your domain and range. There's a specific way that you have to write it. It is a set of numbers. And this is actually true for all sets of numbers. You want to write them a specific way. And the way that I want you to write them is like this. They must go from smallest to largest. So the smallest number on the left, work your way up to the right to the biggest number in order. And then you only ever write them down once. Sometimes, for example, in this particular example, there are elements of the domain and or range that show up more than once. But you only write them down once. In a second here, I'm going to have you write the domain and range out for this relation to make sure we're all on the same page. So a couple things about how to write domain and range, because I'm going to have you do that next. Bless you. Two things. You use braces to write a set of numbers. Okay, braces are what you like to call the squiggly parentheses. Okay, so when we write it, we say domain equals, you put your braces, you fill in with the numbers that are in that domain. For range, you write range equals, braces, fill in the numbers that go. So, for this relation here, I want you to try to write the domain using set notation, and then I want you to try to write the range using set notation and following these guidelines. So do that now. Someone raise your hand and tell me the domain. Yes, sir, David.
-4, 1, 2, 3.
-4, 1, 2, 3. How many of you agree with him? Very good. Now, notice how, even though -4 shows up here and also here, he only mentioned it once, and he went in order from smallest to biggest. Okay? What about the range? Ben, what do you got?
-9, 0, 2, 7, 11.
-9, 0, 2, 7, 11. Okay. That's what you should have had for domain and range. Make sure you follow these guidelines here on a quiz, test, and homework. Inevitably, what ends up happening is people don't put them in order the way I want them to, and they put repeats down. If you do that, I'm going to take points off. Please don't do that. Okay? How many have both of those right? Very good. Domain and range. Easy peasy. Next. Different example. Take a picture of that screen. Probably easier. What's on this screen right now is a similar type thing in a different form. This is called a map. All right? This is a different relation. The numbers are different. And notice, however, the domain is still from smallest to biggest, and the range is from smallest to biggest, we don't write repeats down. You've probably done a mapping before, but we're going to do another one. What this is saying is -4 maps to 5. So how we represent that in a map is we draw an arrow from -4 in the domain to 5 in the range with a little arrowhead. Okay? And you're going to do that for the rest of the numbers, the points in the relation. So go ahead and finish the map. Again, it's one arrowhead, it's a ray. Okay? So it starts at the domain, goes to the range. This is going to come important. It's going to come and play and be more important as we work through the rest of this section today. There should be a total of 5 arrows. Here's what you should have had. Okay, -3 goes to -4. -2 goes to 0. 1 goes to 1. 2 goes to -4. How many had that or something similar to it? Very good. Okay, that's a map. Okay, that's going to come into play a little bit more here in a minute. But sometimes seeing it visually like this helps us make some determinations. Because one of the things that we do with relations is try to decide if they are functions. And then, once we have decided if it's a function, we try to decide what kind of function it is. And this map makes it easier to help figure out. Okay? So let's talk about functions. A function is a special type of relation. So it's under the relation umbrella. Underneath that are functions. It's a special kind of relation. Okay? Each element of the domain maps to exactly one element of the range. In other words, each element of the domain gets used once. Now here in your notes you can use some copying and pasting because I'm going to add to what's below this line from what we just had on our map. Okay? So all I'm doing is adding what was already on the previous slide. Okay? Except for what's here. So notice that this is a function because each x has only one arrow coming off it. Each x is only used one time. Okay? And that's how I know that this relation is also a function. So to reiterate, since each x is only used one time, that's why it's a function. Determining whether or not a relation is a function is always dependent on what's happening with the x. Okay? We'll get into the y's here in a little bit. But the domain, the x's, are what you're going to look at to determine if something is a function. Okay? Now, I'm going to switch off this screen and I'm going to put the original relation that I gave you at the very beginning. So you can copy and paste that back in. And we're going to determine whether or not this is a function. So I want you to copy and paste it from the beginning of your notes. Put it down below and decide if it's a function. And if it is, explain why. If it is not, explain why. Do that now. So the question that you have to ask yourself and be able to answer is there an x that goes with more than one y? And if the answer is no, each x only goes with one y, then it's a function. If there's an x or several x's that go with more than one y, then it's not a function. So is this a function or not a function? Yes, sir.
It is not a function because -4 is paired with both 7 and -9.
Perfect. Perfect. It's not a function because -4 is paired with both 7 and -9. Now, in my explanation, there's an x that goes with more than one y. David's explanation is even better. Okay? -4 goes with both 7 and negative 9. That makes it not a function. Okay? If each x only ever went with one y, then you would say it is a function. Each x only gets used once. Okay? On a test and quiz, you're going to have to explain why something is a function. And you're going to have to explain it from an equation sometimes. You're going to have to explain it from a set of ordered pairs sometimes. And sometimes you're going to explain it from a graph. And we're going to go over all that. So we've talked about determining if something's a function. Now we want to start talking about what kind of function it is. And you're going to want to take a picture of this screen too. Different types of functions. I put 3 up here. There are actually 4. So the explanations up above I think are kind of wordy. And I think I've come up with some explanations that are better. First off, what you have to see here is that we're already talking about relations that are functions. We've already determined that the domains are only used once. Underneath this here, I'm just putting that in. The domains are paired only once. That's the whole worrying about the domain. Is it a function? We're saying, yes, we're already dealing with functions. We've made that first determination. The second part about what kind of function it is has to do with the range. Okay? So, I'm going to put all 3 up, and then I'll explain them at one at a time. Okay, so a one-to-one function means of the elements in the range, they only get used once. So if you only ever use whatever gets used in the range, if it only ever gets used once, then it's one-to-one. Okay, an onto function means it doesn't even matter how many times the range gets used, but so long as they all get used. If they all get used, then it's an onto function. Okay, and then both is literally both. All the range gets used, and they only get used once. That's when we have a both situation. Okay? Now, it doesn't even have to be straight across like this one has. They can certainly cross over. But so long as each one of these is used, and they're each only used one time, that's when it's both. Okay? The fourth one that's not up here is neither. It can be a function, and if the range, all the range doesn't get used, and they don't also get used once, it can be a neither. Okay? So you're going to have to answer that question at some point too. Again, we've made the determination that it's already a function, so x is only used once. It's only paired with one other number, or letter in this case. If each range gets used once, it's one-to-one. If all the range gets used, it's onto. If all the range gets used and they're only used once, it's both. Okay? We're going to talk about that in a problem here in a minute. Go back to our mapping example. This is the same one we already had up here before. Nothing new. It's already in your notes somewhere. Copy, paste it down below. Or for that matter, you can label it up above. I want to know, is this one-to-one, onto, both, or neither? Do that. Figure it out. Okay. In order to be one-to-one, what has to be true? Yeah?
Each domain has to be paired with only one range.
No, that's function. It's all about the range. Remember, one-to-one is all about the range. One-to-one means the range is used how many times? Once. Is there a range that's used more than once? Yes. -4 over here is used more than once. So it can't be one-to-one, which means it can't be both. It could possibly still be neither. Okay? To be onto, all the range has to be used. Is all the range used? Yes. All the range is used. Guess what then? What kind of function is this? It is an onto function. Okay? How many had that? Well, now you're playing the raise your hand game. I see how it is. Okay, good. Let's talk about some more. Let's talk about evaluating functions and function notation. You've done this before. This should be easy peasy. Okay? Just to reiterate, this does not mean f times x. This means f of x. The function's name is f, and x is the input value. This function name is g of x. Its input value is also x. This function's name is h, and its input value is x. What will happen is we'll give you the rule, right? So we have this function named f, and it has a rule, and then we'll give you an input value to insert into that function to come up with a new value, okay? And you've done this before, and it looks like this, okay? So it'll ask you, find the value of f of x. If the rule is f of x equals negative 2x plus 4, if f of negative 1, meaning the input value for x is now negative 1. You've done this before. Do this problem. All right, so we plug negative 1 in for x. Negative 2 times negative 1 is 2. 2 plus 4 is 6. Very good. How many had that right? Good. Let's do another one. A little tougher. Find the value of g of x if the rule is g of x equals 7 plus 3x squared. G of 4. Go. So plug it in. Any of you who tried to multiply 3 times 4 first? Anyone want to do that? Good, because you should not do that. That's 16 times 3 is 48, plus 7 is 55. How many got it right? Good. All right, moving on. There are some more terminology here, okay? If a relation can only be represented by a set of points, then it's considered a discrete relation. Meaning, if you have a bunch of points on a graph, you can't connect them. Because if you connected those points, the space in between them has no meaning for the situation. You have to pay attention to the context of the problem. This will happen in science problems. This will happen in word problems. This will happen in scatter plots, right? There is no meaning in between the points. So you only count the points, not what's in between them. That's a discrete relation. Do you know what the other kind of relation is when you can connect the points? Anybody know? Non-discrete. Very good. No. It's not called non-discrete. You thought you were actually right. No, that's funny. Nope, you're not right. I mean, technically you're not wrong, but that would not get you the final Jeopardy answer correct. Yes. A what? Concrete. You start off so promising. No, but you're very warm. You're much warmer than non-discrete. Continuous. A continuous relation. So what happens there is we can connect the points and there's meaning. If you can connect the points with a line or a smooth curve, then it's considered continuous. Usually you're talking about some type of measurement going on. Okay, like for example, weight is a good example, right? You can't weigh 100 pounds and then the next day weigh 102 pounds and somehow magically skip 100.1, 100.2, 100, right? You have to gain that 2 pounds incrementally, right? You can't just magically skip from 100 to 102, even though maybe some of you think it works like that. It doesn't. Everything in between those weights has meaning, okay? So that's when you can connect the points. There's going to be times when you can't connect points and it's discrete. There's going to be times when you can and it's continuous. The context of the problem will lead you in that correct direction. The next thing is the vertical line test. You're familiar with the vertical line test. The vertical line test is also a way to determine if a relation is a function by using its graph. Okay? There's two ways. Either it's going to be a function or it's not. Right? If it's not a function, the vertical line test is much easier to show and demonstrate. If it is a function, your explanation needs to be a little wordy, and I'm going to give it to you. And make sure that you practice using it, because on a quiz and test, that's the explanation you're going to need. So, here's how we use the vertical line test. If a vertical line, any vertical line, can be drawn on the graph anywhere that hits more than one point, it is not a function. So oftentimes, the vertical line test is best to show that something is not a function. Okay, and then the converse of this is true. If you can never draw a vertical line that ever hits more than one point, then it is a function. And we'll talk about that explanation here in a second. So your first example. Can I draw a vertical line anywhere? Vertical is straight up and down, by the way. Can I draw a vertical line anywhere that will hit more than 1 point in the graph? The blue line. Can you do it? Not there, not there, not there, not there. No, you can't. It's only ever going to hit 1 point, right? That's your explanation. Okay? This is what I want you to write down. And this is what I want you to write down on a quiz or test and on your homework. Homework would be a great place to practice it. It's a function because no vertical line ever touches or hits, I don't care which word you use, more than 1 point on the graph. Do not draw a bunch of vertical lines on there and say, look, it never hits one. Don't draw a bunch of vertical lines on there. It's not going to do it. Because this graph goes on forever and ever and ever and ever to the right. And if you were to draw every single vertical line that ever hit the graph, you would die before you could draw them all. Because the graph goes on forever, there's an infinite number of vertical lines that you could draw, and they would all only ever hit 1 point. So drawing them for a function doesn't do you any good. That's where I have to have this explanation. Okay? When it isn't a function, you can just draw the line and say, not a function. That's kind of the nice part about it when it's not a function. One. Function or not a function? Can you ever draw a vertical line that hits more than 1 point? No, you cannot. This is also a function. I would write the green explanation again, but I don't have the room to do it right now, but that's where you write it again. There's no vertical line that ever touches or hits more than 1 point on the graph. How about this one? Function or not a function? Not a function. So if I draw, so in this case, all I have to do is draw one vertical line and be like, look, it hits 2 points. And then I can write not a function. So when it's not a function, the explanation is so much easier. And I don't even care where you draw your vertical line. Just pick one spot. Show that it hits more than 1 point, and then I know that you get it. Okay? So that's how you use the vertical line test. How many of you have done the vertical line test before, worked with it before? Okay, that's what I thought. All right, let's go through an example. This is the type of problem you're going to see in your book. You can take a picture of this, and we're going to work through all of this together. This problem is literally everything. Everything that we just talked about synthesized into one problem. Okay? We're going to graph the line. We're going to determine domain and range. We're going to figure out if it's a function, and if it is, what kind of function. We're going to decide if it's discrete or continuous. So there's a lot to do on this problem. None of it is hard, though. Okay? Graphing the line. You have two options. You can make a table of values, or I'm super vague here about graph using linear equation strategies, because this is a linear equation. If you remember your stuff about slope and y-intercept and that kind of thing, you're welcome to use that. That's coming later in this chapter, so I'm pretending that you don't know how to do it, and I'm going to teach it to you. However, I know you've learned it. So if you think that graphing using slope and y-intercept is easier than making a table of values, you are welcome to do that. All right? However, for my example, right now I'm going to use a table of values because, like I said, I'm going to teach you about linear equation strategies here later on this chapter. So, my table of values, you make an x, y, and you pick a bunch of x's, plug them in, find the y's. Now, probably what you've done in the past is you said x, and you go 0, 1, 2, and you plug them in and see what you get. Here's why I'm not going to use 0, 1, 2. I notice that whatever value I plug in for x has to get multiplied by a half. So if I plug odd numbers in here, like 1, I'm going to be dealing with fractions. And I know that I don't want to deal with fractions, and I certainly know that you don't want to. So instead of picking odd numbers, I decided to pick even numbers. Because all of those x's being multiplied by 1/2 will give me an integer, a whole number, a natural number, okay? Which will make my math a lot easier. So when I plug 0 in, this all goes to 0 minus 3 is what? Negative 3. When I plug 2 in, 2 times 1/2 is what? Minus 3, negative 2. What's the next one going to be? Follow the pattern. Negative 1. Okay? So there's my table values. Then I put those on a grid. Then I connect the dots and I make a beautiful line. Okay? Goes on and on forever in both directions. The next thing I'm going to do is find the domain and range. Here's how you do that. Bless you. Bless you. Go for 3. Nope. Okay. So here's how you do that. You look for spots where there might not be an X. So if I travel on this long, let's think for a minute that I could travel on in both directions. Would it ever not have any X's? Would there ever be an X that you couldn't find on the line somewhere eventually? So if I traveled this way, is 20 for X gonna be on that line somewhere? Will it touch somewhere over here? For sure. Will 100 somewhere be on this line? How about if I go the negative direction? All these numbers are on the line somewhere. Might have to go down below the screen on the board. There it goes. But there's always going to be an X. Every single X that you could think of will be on that line somewhere. So that tells me the domain is all real numbers. Okay, there's no holes in the line. There's no right or left boundary. It goes on and on, boundless in either direction. I look at it the same way for Y, for the range. Is there ever a value going up or down that won't hit this line? If I could extend it forever and ever. Right, there's not a lower boundary. This just keeps going down and down and down, which means it will hit every single Y. Over here, it keeps going up and up and up, and it's going to hit every single Y up here. So in this case, there's no holes in the graph. There's no right or left boundary. There's no upper or lower boundary. So my domain and range are all real numbers. And remember the little script R I showed you earlier. Do not write ARN. That's not a math thing. Okay? So that's my domain and range. Is this a function? So think about vertical line test. If I draw a vertical line on this graph, is it ever going to hit the line in more than one place? No. No, it is not. This is a function. What kind of function? So here it gets tricky, right? Because the domain is all real numbers, the range is all real numbers. Is there ever an X that can get used more than once? Okay. Is there ever a range that can get used more than once? Is there a Y that can get used more than once? Nope. So each Y gets used only once. Do all the Y's get used? So therefore it is a both. Discrete or continuous? Is it just a bunch of points or is it a line or smooth curve? Line. So therefore it is continuous. Okay?